Welcome to this coding problem walkthrough. Today, we will explore a fascinating problem titled KTH smallest number in multiplication table. We'll break down the problem, examine potential approaches, and understand the most efficient way to solve it. Let's dive in. The problem asks us to work with a multiplication table defined by two integers, m and n, representing the number of rows and columns, respectively. In this table, the value at any cell, I, j, is simply the product of its row and column indices, I*j. Our goal is to determine the KTH smallest number in this mxn multiplication table when all the values are sorted in ascending order. The input includes m, n, and k, where m and n can range from 1 to 300, and k is guaranteed to be a valid position within the table, meaning it falls between 1 and m*n. The output for the problem is a single integer, which is the KTH smallest value. With this setup, we are essentially tasked with efficiently searching for a specific number in what can potentially be a very large multiplication table. Let's look at an example where m is 3, n is 3, and k is 5. This means we have a 3 by 3 multiplication table. When we expand this table, the rows and columns form products like this: row 1 contains 1, 2, 3, row 2 contains 2, 4, 6, and row 3 contains 3, 6, 9. If we sort all the numbers in this table in ascending order, we get the sequence 1, 2, 2, 3, 3, 4, 6, 6, 9. Since we need the fifth smallest number, we look at the fifth position in this sorted array, which gives us the value 3. So, the output for this case is 3. Now, consider another example where m is 2, n is 3, and k is 6. Here, the multiplication table is smaller, with 2 rows and 3 columns. The table looks like this: the first row contains 1, 2, 3, and the second row contains 2, 4, 6. Sorting all the numbers in the table results in the sequence 1, 2, 2, 3, 4, 6. To find the sixth smallest number, we check the sixth position in this sorted sequence, which gives us the output of 6. For a larger example, let's take m as 300, n is 300, and k is 100. The multiplication table in this case is massive, containing 300 rows and 300 columns. Despite its size, we can still determine that the 100th smallest value in this table is 10. The solution achieves this efficiently without directly generating or sorting the entire table, which would be computationally expensive. To solve the problem efficiently, we use a binary search approach. The central idea is to determine how many numbers in the multiplication table are less than or equal to a given value. This count allows us to adjust our binary search range, gradually narrowing down to the KTH smallest number. This method avoids the need to explicitly generate and sort the entire table, making it suitable even for very large inputs. Additionally, we must consider edge cases, such as when m or n is 1, reducing the table to a single row or column, or when k is at the extreme ends of the range, where the smallest or largest number in the table is the immediate answer. To solve the problem of finding the KTH smallest number in an mxn multiplication table, one approach is to use brute force. The intuition here is straightforward: we generate all the elements of the multiplication table explicitly, sort them, and then pick the KTH smallest element. The steps involve calculating every possible product of row and column indices, storing these products in a list, and then sorting the list. While this method is simple to understand and implement, its main drawback is inefficiency. Specifically, for large values of m and n, the table becomes enormous, and sorting it consumes significant computational resources. This results in a time complexity of O, m*n*log, m*n, and a space complexity of O, m*n, making it impractical for larger inputs. In summary, while the brute force method works, it doesn't scale well for larger tables, which is why we need a more optimized solution. A more efficient approach utilizes binary search on the answer space. The key insight here is that the multiplication table has a structured property: each row is sorted, and values increase as you move down columns. This allows us to avoid generating the table explicitly and instead focus on narrowing down the KTH smallest number through binary search. The process starts by defining the search space between 1 and m*n, which represents the smallest and largest possible values in the table. For each midpoint in this range, we count how many numbers in the table are less than or equal to the midpoint using a helper function. This counting function iterates through each row and adds the smaller of x divided by the row index or the column limit, n. If the count is greater than or equal to k, we know the kth smallest number is smaller or equal to the midpoint, so we adjust our search range accordingly. Otherwise, we search in the higher range. The binary search continues until convergence, efficiently pinpointing the kth smallest number. This approach achieves a time complexity of O, m log, m n, and uses only constant space, making it significantly faster and more scalable than brute force. The chosen strategy for this problem is the optimized binary search approach. This method stands out because it avoids the inefficiencies of the brute force approach by leveraging the inherent structure of the multiplication table. Instead of explicitly generating and sorting the table, it uses binary search and a counting function to directly find the kth smallest number. This makes it both time efficient and space efficient. However, there are trade-offs to consider. While the brute force method is intuitive and easy to implement, it becomes computationally infeasible for large inputs. The optimized binary search, on the other hand, requires a deeper understanding of the table's structure and binary search concepts, which might make it less accessible for beginners. The key insight, or aha moment, that drives this approach is recognizing the sorted nature of the table and the ability to efficiently count elements less than or equal to a given value without generating the table. This insight allows us to narrow the search space effectively and solve the problem in a highly efficient manner. In conclusion, the optimized binary search approach is the most scalable and efficient solution for finding the kth smallest number in a multiplication table. It achieves a balance between computational speed and memory usage while avoiding the inefficiencies of brute force methods. By taking advantage of the table's sorted structure and using binary search to limit the search space, this method provides a highly effective solution. This approach not only demonstrates the power of leveraging problem-specific properties but also highlights the importance of optimizing both time and space complexity for large-scale problems. To solve the problem of finding the kth smallest number in an mx and multiplication table, we start by understanding the structure of the table. Each cell in the table at row I and column j contains the product of I and j, and both rows and columns are indexed starting from 1. A straightforward approach to solving this is to generate all possible values in the table, sort them, and then directly retrieve the kth smallest value. The intuition here is simple: by generating all combinations of products, we can systematically organize them to locate the desired element. The first step in this process is to iterate through all row indices from 1 to m, and for each row, iterate through all column indices from 1 to n. For every combination of row and column, we calculate the product and store it in a list called values. This list will eventually contain all the elements of the multiplication table in an unsorted form. Once we have the list of all products, the next step is to sort it in ascending order. Sorting ensures that the elements are arranged from the smallest to the largest, making it easy to retrieve the kth smallest element. After sorting, we can directly access the element at index k1 in the list, as most programming languages use zero-based indexing. This step completes the process of finding the desired value. The reason sorting works lies in its ability to organize the data sequentially. By definition, the kth smallest element in a sorted list is precisely the kth value. The data flows through the algorithm in 3 stages: generating the list of products, sorting the list, and accessing the required element. While this approach is straightforward to implement, it's important to consider its efficiency. Generating the multiplication table involves iterating through all mxn combinations, and sorting the resulting list adds additional computational overhead, which we'll analyze further. The time complexity of this brute force approach can be broken down into 2 main components. First, generating the multiplication table involves O, m n operations, as we compute all possible products. Next, sorting the list requires O, p log p, where p is the total number of elements, which equals m n. Combining these, the overall time complexity becomes O, m n plus m n log, m n. For space complexity, the algorithm uses a single list to store all the values, which requires O, m n, space. Sorting is performed in place, so no additional significant space is needed beyond the list itself. A list is chosen as the primary data structure because it offers efficient random access, making it ideal for retrieving the kth element once the list is sorted. Additionally, the sorting algorithm used depends on the programming language. For instance, in Python, the built-in sort method uses timsort, which has an average case complexity of n log n. Despite its simplicity, this approach faces challenges with edge cases and performance on larger inputs, which we'll discuss next. When analyzing edge cases, a few scenarios stand out. First, if either m or n equals 1, the multiplication table reduces to a single row or column. In such cases, the algorithm still functions seamlessly since the list is inherently sorted, and no additional sorting is required. Another scenario occurs when k equals m asterisk n, meaning we are looking for the largest element in the table. The algorithm handles this naturally, as sorting ensures that the largest value is positioned at the end of the list. Additionally, duplicate values in the table, such as 2 by 3 and 3 by 2 both yielding 6, are grouped together during sorting, so duplicates do not affect the accuracy of the result. However, for very large values of m and n, such as 10,000, the brute force approach may become computationally expensive due to the sheer size of the multiplication table. This highlights the need to optimize the algorithm for better performance on large inputs. To summarize, the pseudocode for this approach involves generating the list of products, sorting it, and returning the kth smallest value. Here is the complete pseudocode. We define a function that takes m, n, and k as inputs. First, we initialize an empty list called values. Using nested loops, we iterate over all row indices from 1 to m and all column indices from 1 to n, computing the product of I and j and appending it to the list. After generating the list, we sort it in ascending order. Finally, we return the element at index k1, which corresponds to the kth smallest value. The time complexity of this approach is dominated by the sorting step, making it m asterisk n log m asterisk n, while the space complexity is m asterisk n, due to storage requirements for the list. While this brute force method is simple to implement and handles edge cases well, its computational demands on large inputs suggest that more efficient algorithms, such as binary search, may be better suited for scaling. This concludes our step-by-step breakdown of the brute force approach. This implementation solves the problem using a binary search approach. The core idea is to find the kth smallest number in the multiplication table without explicitly constructing it, as the full table can be very large. The find kth number function starts by defining a helper function count less equal x that calculates how many numbers in the table are less than or equal to x. For a given row I, the maximum value that can fit into x is x / I, but this should not exceed n, the number of columns. Summing this up for all rows gives the total count of numbers less than or equal to x. The left and right variables represent the binary search range. Initially, left is set to 1, the smallest number in the table, and right is set to m asterisk n, the largest number in the table. The binary search loop continues until left equals right. Inside the loop, the midpoint mid of the range is calculated. If the count of numbers less than or equal to mid is less than k, it means the kth smallest number must be greater than mid. Therefore, we adjust the range by setting left equals mid plus 1. Otherwise, we reduce the range by setting right equals mid. When the loop exits, left contains the kth smallest number, which is then returned as the result. This approach is efficient, with a time complexity of m asterisk log m asterisk n, where the binary search runs in log m asterisk n, and the helper function iterates through all rows m. This makes it suitable for the problem's constraints of large m and n, up to 300. This is the Java implementation of LeetCode problem number 668, kth smallest number in multiplication table, using binary search to efficiently find the kth smallest number. The logic mirrors the Python implementation, with Java-specific syntax such as type declarations and the math library. The helper method count calculates how many numbers in the table are less than or equal to a given value, enabling binary search to narrow the range and locate the desired number. In this example, we are tasked to find the fifth smallest number in a 3 by 3 multiplication table. First, we initialize our binary search range with left set to 1, which is the smallest value in the table, and right set to 9, the largest value, calculated as m asterisk n. For the first iteration, we calculate the midpoint as mid equals 1 plus 9 / 2 equals 5. To determine how many numbers are less than or equal to 5 in this table, we use the count less equal function. This function iterates over each row to calculate the contribution of numbers less than or equal to 5. For the first row, the minimum of 5//1 and 3 is 3. For the second row, the result is min, 5//2, 3, equals 2. Lastly, for the third row, the result is min, 5//3, 3, equals 1. Summing these up, we get a total count of 6 numbers less than or equal to 5. Since the total count of numbers less than or equal to 5 is 6, which is greater than or equal to our target k equals 5, we update the right boundary to mid, making right equals 5. In the second iteration, we calculate a new midpoint as mid equals 1 plus 5//2 equals 3. Using the count _ less _ equal function again, we calculate the count of numbers less than or equal to 3. For the first row, the contribution is min, 3//1, 3, equals 3. For the second row, it is min, 3//2, 3, equals 1, and for the third row, it is min, 3//3, 3, equals 1. This gives a total count of 3 plus 1 is equal to 5. Since this count is still greater than or equal to k, we update right to mid, making right equals 3. In the third iteration, we calculate mid equals 1 plus 3//2 equals 2. Calling count _ less _ equal 2 gives a count of 2 from the first row, 1 from the second, and 0 from the third, resulting in a total count of 3. This time, the count is less than k, so we update left to mid plus 1, making left equals 3. Now that the binary search has converged with left equal to right, we conclude that the fifth smallest number in the table is 3. For the next example, we'll determine the fourth smallest number in a 2 by 3 multiplication table. The table looks like this: 1, 2, 3, 2, 4, 6. We begin by initializing left to 1 and right to 6, the largest value in the table. For the first iteration, we calculate mid equals 1 plus 6//2 equals 3. Using the count _ less _ equal function, we calculate the number of values less than or equal to 3. For the first row, we get min, 3//1, 3, equals 3, and for the second row, min, 3//2, 3, equals 1, giving a total count of 4. Since the count matches our target k equals 4, we update right to mid, setting right equals 3. In the second iteration, we calculate a new midpoint as mid equals 1 plus 3//2 equals 2. Using count _ less _ equal 2, we find there are 2 numbers from the first row and 1 number from the second row that are less than or equal to 2, giving a total of 3. Since the count is less than k equals 4, we update left to mid plus 1, making left equals 3. At this point, the search converges with left equal to right, and we determine that the fourth smallest number in the table is 3. Now let's consider a larger table, where m equals 4, n equals 3, and k equals 8. The table looks like this: 1, 2, 3, 2, 4, 6, 3, 6, 9, 4, 8, 12. Using the same binary search approach, the search narrows down to left equals 6 and right equals 6 after several iterations. The final result for this example is that the 8th smallest number in the 4 by 3 multiplication table is 6. Throughout the binary search process, we efficiently narrow down the range, left, right, by repeatedly splitting it in half and counting the numbers less than or equal to the midpoint. The count _ less _ equal function is pivotal here, as it allows us to compute the count row by row, ensuring the calculations are efficient even for larger tables. Depending on whether the count is greater than or less than k, we adjust either the left or right boundary to hone in on the target value. This method continues until the left boundary equals the right boundary, at which point we have successfully identified the kth smallest number in the multiplication table. By leveraging binary search and the efficient row-wise counting approach, we solve the problem in a way that balances clarity and computational efficiency, even for larger values of m, n, and k. To analyze the time complexity of our solution, we break it down into 2 main components: the binary search and the counting function. First, consider the binary search. It operates over a range of possible values, starting from 1 and going up to m times n, where m and n are the dimensions of the multiplication table. With each iteration, the search space is halved, which means the number of iterations is proportional to the logarithm of the range size, resulting in a complexity of O log m*n. Next, for each midpoint value during the binary search, there's a need to count how many numbers in the multiplication table are less than or equal to that midpoint. This is handled by the count_less_equal function, which processes each of the m rows in the table. For each row, it calculates the count of valid values using a simple formula, mid divided by the row number, n. This calculation is constant time per row, so counting across all rows has a complexity of O(m). Combining these two parts, the binary search with O, log, m*n, iterations and the counting function with O, m, complexity per iteration, the overall time complexity becomes O, m*log, m*n. Now, let's consider the space complexity of this solution. It is highly efficient because we only use a few variables to manage the binary search and counting process. These are the bounds of the search range, namely left and right, the midpoint value, mid, and a counter to store the result of the counting function. Since no additional data structures, such as arrays or matrices, are used, and no recursive calls are made, all operations are performed in constant space. This gives us a space complexity of O(1). Additionally, when we analyze the best, average, and worst cases, the computational effort remains the same. Regardless of the position of k within the range, the binary search must fully converge to pinpoint the kth smallest value. This means the time complexity remains consistent at O, m*log, m*n across all scenarios. Finally, let's compare this optimized approach to a brute force method. A naive solution would involve generating the entire multiplication table, which has m times n entries, then sorting this table and extracting the kth smallest element. Generating the table takes O, m*n, time, and sorting it adds a complexity of O, m*n, log, m*n, resulting in a total time complexity of O, m*n, log, m*n. Furthermore, the space complexity of the brute force approach is O, m*n, since the entire table needs to be stored in memory. In contrast, our optimized method avoids generating and sorting the table altogether. Instead, it uses binary search combined with row-wise counting to reduce the time complexity to O, m*log, m*n, and the space complexity to just O(1). This is a significant improvement, especially when m and n are large. The optimized solution achieves this by leveraging the logarithmic reduction of the search space in binary search and the efficient row-wise counting process. With this, we achieve a highly efficient solution in both time and space, making it far superior to the brute force alternative. Here we outline some common mistakes that can arise when solving this problem. First, not accounting for duplicates in the multiplication table is a frequent error. Since values like 2 times 3 and 3 times 2 are identical, failing to handle these duplicates can lead to overestimating the unique numbers in the table. This impacts the accuracy of our index calculations, making it harder to correctly pinpoint the kth smallest value. Another common pitfall is using a brute force approach to generate and sort the entire multiplication table. While this might seem straightforward, it becomes computationally expensive for large inputs, say a table of size 10,000 by 10,000. This method has a time complexity of O, n squared log n, and can even result in memory overflows. Similarly, setting improper binary search bounds is problematic. If the bounds are too narrow, such as limiting the range to 1 through n instead of the full range of 1 through m times n, the algorithm might overlook valid kth smallest elements. Finally, failing to leverage the sorted nature of rows and columns in the multiplication table often leads to unnecessary complexity. Ignoring this structure means your solution might not take advantage of the inherent properties of the table, leading to inefficient computations. Now, it's important to address edge cases and interview specific insights. For instance, small tables can introduce unique challenges. Special cases like k being equal to 1, k being equal to m times n, or tables where either m or n is 1 often require additional handling to ensure your solution remains robust. When it comes to interviews, a key insight is recognizing that the multiplication table is essentially a sorted grid. This allows us to use efficient techniques like binary search on the value range, rather than generating the entire table. The optimal approach involves performing binary search between 1 and m times n, while using a helper function to count how many elements are less than or equal to a chosen midpoint. This approach not only optimizes the search space but also demonstrates your ability to adapt known algorithms to new contexts. During interviews, it's essential to clearly communicate why brute force methods are impractical for large inputs and to explain how binary search significantly reduces computational overhead. Highlighting patterns, such as this problem's similarity to the kth smallest element in a sorted matrix, can further showcase your problem-solving skills. This problem also shares connections with other related challenges in algorithmic problem-solving. For example, LeetCode 378 focuses on finding the kth smallest element in a sorted matrix, which is conceptually similar to the multiplication table problem. Similarly, LeetCode 719 tackles finding the kth smallest pair distance, and LeetCode 240 involves searching within a 2D matrix. Exploring these problems can deepen your understanding of similar techniques. As for alternative approaches, one option is using a priority queue, or min-heap, to track the smallest elements row by row. While this method is simpler to implement, it becomes less efficient than binary search for large tables, with a time complexity of k log n. Another approach involves flattening the multiplication table into a single list and sorting it. While intuitive, this method is computationally expensive, with a complexity of m times n log m times n, making it unsuitable for large inputs. The most efficient method remains binary search on the value range, combined with a counting function to determine how many elements are less than or equal to a midpoint. This approach, while optimal, requires careful implementation to ensure the counting logic is both correct and efficient. Great job following through to the end. In this session, we summarized the key approach to solving the kth smallest number in multiplication table problem. Remember, brute force is a starting point, but exploring optimized solutions like binary search can elevate your problem-solving skills. Thanks for watching, and see you in the next video. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!